Hey, my name is Ismail Garcia, and for my quantum project, I'm implementing Bernstein-Vazirani's algorithm. So quantum computers are the next big leap in processing and problem-solving technology. They're kind of like the next generation of computers. But a common misconception with quantum computers is that they're simply just supercomputers. That is to say, more powerful versions of regular computers. However, quantum computers are almost like a whole different tool than regular computers. See, a regular computer is kind of like a hammer, and a quantum computer is more like a screwdriver. While they can both be used to fix and build things, they do very different jobs. Quantum computing is a special type of computer that thinks in a different way than normal everyday computers. See, normally computers understand information by turning everything into either zeros or ones. For example, if you take the letter A, computers read the capital letter A as 0, 1, 0, 0, 0, 0, 0, 1. Since computers can only understand zeros and ones, we have to tell them how to arrange the order of the numbers so that they can understand different things. So, in this example, let's use coins to represent every number. For the letter A, there are a total of 8 zeros and ones together. So we can have 8 coins and make all the zeros heads and all the ones tails. If we put the coins in order of heads, tails, heads, 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 tails, your computer will understand that specific order as the letter A. Now, here's why quantum computers are special. What quantum computers do is that they have an extra trick in their toolbox. They can take the coins and they can spin them. This means that they don't have to choose heads or tails. They can have both. This is a rule known as superposition, where it can be a combination of both heads and tails, both zeros and ones. Another ability that quantum computers have is entanglement. So going back to our coin example of how entanglement works, it's like having the two coins connected to each other. If one is heads, the other is also heads. They work in a system, mirroring the other's attributes. A third big property of quantum computers is interference. So interference allows control over the quantum states. They can amplify signals heading towards the right answers and cancel out signals heading towards wrong answers. There are two types of interference. The first is constructive interference, where wave amplitudes add together. If a wave is giving us the right answer, we're going to add to the wave to make it bigger and stronger to help us get the answer correct. The second is a destructive interference, where the amplitudes cancel out. If a wave is pointing towards the wrong answer, then we can just send another wave to interfere, weaken, or even just block out the signal entirely. This works kind of like how noise cancelling headphones such as these, where the waves are blocked or they bounce off of them. In the case of headphones, headphones use microphones to pick up noise, and then they send back a signal that blocks the noise out. This is done by taking whatever wave is coming in, inverting it by 180 degrees so that the exact opposite wave is being sent out, and that then cancels both of the waves out, thus making the headphones cancel out noise. So all these properties means that a quantum computer can solve problems just way faster than any computer that exists today. Okay, so to give an example of how quantum computers work, the program I implemented follows Bernstein-Vazirani's algorithm. So the purpose of this algorithm is to figure out an unknown encoded string given n number of bits in the string. So a normal computer can figure this out in n number of tries, whereas a quantum computer can figure it out in just one try using this algorithm. So to start off, we're going to import all of the library and tool necessities here, such as Qiskit and its histogram plots. Then what we're going to do is we're going to provide the hidden string here and its respective number of bits, which is equal to n. So what we're doing is we're assigning 3 qubits to the value of n. So then we're going to have the main function of the circuit here, and what we're going to do is that we're going to first create a circuit, and we're going to assign the number of bits to it. So the first value here in the circuit is n plus 1, where this is the number of bits, the qubits being assigned to it, and this plus 1 is known as an ANSIA qubit, and ANSIA bits are extra bits used for specific goals in quantum computation, such as reversible computation. In the case of Bernstein-Vizirani's algorithm, the ANSIA bits are used for storing the entangled states, and they are also used for error correction and preventing noise interference. The second value here is the n number of classical bits that's going to be used as your output. So next what we're going to do is we're going to assign H gates and Z gates for each qubit. The H represents Hadamard gate, which what the Hadamard gate does is it places a qubit in superposition and generates a 50-50 random chance of measuring either a 0 or a 1. The Z gate, what it does is it tells the qubit to rotate by 180 degrees, which produces the opposite wave. For future reference, the barriers are just a visual thing used to separate it here in the circuit. They don't do much. So after that, what we're going to do is we're going to go through and we're going to reverse the output. This is because the circuit is built from this top-down view. So the first bit that you encounter is going to actually be the bottom bit. So what we have to do is we're going to take all the bits in S, and then we're going to, as you read them, reverse the order that we're reading them. So what we're going to do now is we're going to have the for loop. We're going to have a for loop running through every single qubit, and we're going to check if it's a 0, then we're just going to return the value as is. Otherwise, if it's a 1, we're going to add a control X gate, which is the quantum equivalent of adding a NOT gate. So it's going to inverse the bit that it is. So if it's a 0, it's going to flip it to a 1. If it's a 1, it's going to flip it to a 0. So after that, it's just going to be followed by another barrier, and then some more Hadamard gates afterwards. Finally, what we're going to do is we're going to measure the output, and so we can read the bits that it's giving us. So for every single bit, we're just going to measure what the output is so we can read the data and then spit out what the final answer is. And then this line just allows us to print out this circuit for us to see what our quantum circuit looks like. So now what we can do is we can run the circuit through a local simulator via this code, and it's going to plot it on this histogram. So here we can see that it had correctly solved the string with 100% probability because this is in a perfect simulated environment. It's always going to guess it right. So finally, what we can do is that we can use this section of code to run the program on an actual quantum computer via IBM servers. So this code is just to load into the account and then set up your server, and then here is just picking the least busy server to run the code through. So I'm going to go ahead and just run the code to see what it gives us. So it's running through the code and it's showing the diagrams, and it picked the least busy server, which currently is this, and right now the job is actively running, so it's going to take a minute and it's going to run it through the quantum servers. So once the job is done, what we're going to do is we're going to store the results here, and then we're going to plot that onto the onto a histogram, and we'll see we can compare the simulated one to the actual quantum results. Okay, so the job finished running and it finally got the results from it. So here we can see that it plotted the histogram, and we can see that in a real case scenario the system was able to solve the string with a majority success rate, and we had it set to 1,024 trials. We can see here that the initial system obviously had a 100% success rate because it was a simulated environment, so there was no kind of interference or any kind of error whatsoever, and it was able to guess the string, which we had set to 010, which it guessed it was 010, and it figured that out. Whereas when this is running in the quantum environment here, we see that there were some errors returned by the system, obviously due to like the many complications, and quantum technology is still in early days of development, so it's still imperfect, but you can still see that in an overwhelming 87% of cases it did pick the correct string as 010 as well. So that concludes our overview of quantum computing and the Bernstein-Vazirani's algorithm. Thank you very much, and goodbye.